In this video, we're going to go over some special examples of linear transformations that we will either use in examples later on or things that you may have seen before and now we can identify them as linear transformations. The first is in some sense one of the boring ones. It's called the identity linear transformation. And it's the linear transformation where the output is just always the same as the input. It's like the line y equal to x, right? Output and input are always the same. The function's not really doing anything. And we mainly want to talk about this when we're talking about inverses. You need to have identity to make sense of an inverse. Regardless, there we go. The second one is called the zero linear transformation. Again, this is maybe one of the more boring ones. This one is the idea is that no matter what your input is, the output is always going to be 0. So again, just input, no matter what it is, the output is going to be 0 here. The next one is actually, I think, pretty interesting here. This next one is talking about what happens if you want to rotate something, right? We rotate things all the time in the real world. As the most simple example that you encounter all the time, the wheels on your car are rotating, right? So we go ahead, we're going to rotate these things, and we want to describe that mathematically. We're going to use this matrix here, cosine theta minus sine theta, cosine theta. Now that is specifically for a specified certain value of theta, whatever it may be, 30 degrees, 90 degrees, whatever your favorite angle is. And if you pick a different angle, you're going to get a different matrix. But regardless, this is the general formula for how you do a rotation in R2. So again, if you were to plug in, say, I don't know, 30 degrees here, and if you know all your trig values, you could work that out, what those numbers are. But if you did that and you drew your picture, and you started with one vector here, then you apply your linear transformation, and the output vector would just be the same length, but 30 degrees different in the angle. Again, the rotation matrix is hugely important. I've seen it used in physics classes. I've seen it used in engineering classes. I've seen it used in actually programming of video games, right? You have things moving around the screen. So very often this matrix is used. Definitely one to know. The next one here, this one's a little bit odd at first. It takes in a three-dimensional vector x, y, z and spits out a two-dimensional vector x, y. This is what's called a projection. Now this is not the only projection out there. There's just one of many of them. But the idea of a projection is you take a vector in some three-dimensional or a higher dimensional space, and you imagine like shining a light straight down and trying to see what happens in just the xy plane. And this resulting vector down here, that's the projection. You're projecting down, like again, a shadow, or its projection. You're projecting it down to 2 dimensions, and this is the case where it's xy. So if you ever have a problem where you're trying to solve something involving three-dimensional shape, but you want to break it down into two-dimensional shapes instead, this is what you're going to use. You're going to use a projection map to get the answer there. It's a very useful thing. And again, this is not just the only projection map. There are many other ones out there, but this is the one example that we're choosing to use here. Now the next one is an example from calculus. And again, maybe you've had calculus, maybe you haven't had calculus at this point in time. But there are two quick examples here. First off, if you take a function, say f of x, as your input, and your output is the derivative of that, and as long as you're in a vector space where a derivative makes sense, then this is actually going to be a linear transformation. So the derivative is a linear transformation. Also, if you do an integral, specifically a definite integral, that is also going to be a linear transformation. And so at some point in time in your calculus class, they would have asked you, like to prove the linearity properties of the integral, where if you take the derivative of two things, you add them, and so on, all the different rules from the properties of calculus that you may have skipped over there or didn't pay much attention to. All of those were really showing that the derivative and integral are linear, and in particular, they are linear transformations here. Now, we aren't really going to use those right now, but they are good examples to keep in mind. And then at the end of the day, I gave you this big theorem here. It's actually very, very important. In the previous video, we were testing things, whether or not something was a linear transformation, and we had to either prove two things work or go ahead and find an example where things don't work. And the thing is sometimes it was really annoying there, but it turns out this theorem tells us that if you can write your function as a matrix times the input, if you ever can find a matrix to make this work, that means it's a linear transformation. And if you can't find a matrix to make it work, that means it is not a linear transformation. So in some sense, all linear transformations are matrices, and all matrices are linear transformations. So it's all interconnected here, which is why when we study matrices for a long time, we are actually getting information about linear transformations all in the same work. We don't have to do any additional work there.